what would this look like? What do we mean when we say such a thing? Here's what we mean. We mean r of t, right, is, well, r cosine theta, r sine theta. It's just now the theta and the r are written in terms of t. Okay? So this would mean, t squared cosine of cosine t, ooh, and then t squared sine of cosine t. That's what that means. One of your homework problems is to show that the speed squared, all right, in other words, dr dt dot dr dt, if you work it out, it's equal to r dot squared plus r squared theta dot squared, where r dot is equal to dr dt, and theta dot is equal to d theta dt. This is notation that goes back to Newton, the dot derivative for time derivatives. But that's a formula for the the speed squared in polar coordinates. Let me just write it up here again. V squared. So this one of your homework exercises is to work that out. It's just a chain rule, really. And the calculation is very, very similar to what I did on the rightmost board. It involves just doing the chain rule, squaring both things, and noticing that like the cross terms cancel. When you get into it, you'll know what I'm saying. Yeah. Time derivative. So r dot is dr dt. Notice that in this context, both r and theta are functions of time, t. So I just want to, a lot of you are taking, physics 231 right now, right? So just to try to connect back to that course again momentarily, this would be the tangential component of the velocity squared. This, if you remember the radial part of the velocity, is equal to, oh, I'm sorry, other way around. I'm an idiot. I've got it totally backwards. This is the radial part of the velocity squared. Duh. Good grief. People, listen to me. Yowzers. Radial. Because it goes with the radius, right? Duh. Radial. This, on the other hand, is the tangential part squared. Remember, Vt is what? Vt is r omega. But here, omega is the change in theta. So to find the, speed squared for an object in both rotational and linear motion in a plane, you can take the tangential component of the velocity squared and add it to the radial component of the velocity squared. That gives you the speed, the speed squared for the motion, which, if we have in terms of angular velocity omega, is just exactly this. Okay, anyway, that's just, sorry, 2 minutes on physics there. Let's see if this will this do it? If I say r equals to t, theta equals to cosine t, will it play along? Points are written, yeah, okay, great. I don't know, there may be, so I'm not sure what's the the laziest way to do it with Desmos, but here's how I'll do it. Doubtless there are software packages to plot these things with less coding, but here's a way. And let's let t range from 0 to a, because then we can play. Ooh, here, let me zoom out a bit. Whee! Want me to make it, here, I'll make it rotate around the origin. Check this out. Just add a cosine t. See what that's doing is adding a circular base point. That makes cosine t sine t as its sort of origin, so to speak. So that's going to rotate the curve we're looking at. Hey, come on. Oh, I know the problem. T squared's too big. Phooey. I know what I got to do. Oh, curses, that's the wrong way to think. Huh. I guess I got to put it, well, if I put yeah, okay, fine, t squared. Oh, it doesn't like that. Oh, which one? I don't know. It's fun to play with these sorts of things. What I'm fond of.
You should find out ways to make art with it and then sell it to people. It's like all modern art, and then like give them all the.
You know, there are people who make their side gig is making mathematical art.
Just say that has like profound connections to human understanding.
It has profound connections to human understand. Okay, well, yeah, sure, why not? What? Whee! It was there. It was there all along. So, in some sense, this is a picture of what modern physics thinks. Like a lot of theoretical physicists think that everything interesting is happening where we can't see it. Kind of like this curve. Yeah. But if we zoom in, all the way down. Oh no, we got off center. No, we lost it. Oh, there it is. What happens if I? Oop. I think at some point we're probably going to fall prey to the dreaded machine epsilon and numerical this and that. But well, computers don't do continuous arithmetic, right? Like there's no real number on a computer. There's only floating point representations of numbers, which can only get to be so small, right? Epsilons and deltas only works on the board. It doesn't work on the computer. Oh, so tomorrow, I think I've actually said probably about everything I need to say about polar coordinates. I think I'm going to turn the page and at least introduce the Fourier series idea tomorrow, and that's our final topic for this semester. So we should have more time to discuss polar coordinate stuff next week. I'll be gone part of next week, so tomorrow we'll talk about when the final is, okay?